I hope you can see my screen. So maybe we will wait for 1 or 2 minutes, and after that we will start so that people will join. Okay, maybe we can start. So today we will talk about the assignment 2, week 2, nuclear and particle physics course. So whatever it was there for the last week, it was first assignment 1 and assignment 0. But today we will talk about assignment 2, which was for the week 2. And obviously that is the previous year question paper. Okay. So is there any doubt for the assignment 1 this year? I think the deadline has already gone. If it has not gone yet, then I will not tell anything about this assignment 1 questions, but if the deadline has over, then I can explain this one also. So if you have any doubt about the assignment 1, you can just text me. I think it's automatically joining. Yes, it's automatically joining, so it's fine. So if you have any doubt for the assignment 1, week 1, if it has the deadline over, then we can talk about this. There is something in chat box maybe. Deadline is 7th August. Okay, then I will not tell anything. Okay. So yeah, fine. And for the assignment 2, I think the more deadline will be there. So right now we will just talk a little bit more about the previous year assignment. Then it will help you for doing this year assignment as well. Okay. So before going to there, I just have a picture here which we will use throughout the today's session. I mean, today's 2-hour session will be basically based on this figure. And so last time there was one girl who was asking for the magic number concept through the, I think it is automatically joining. Okay, then I should not come here. So here this picture, whatever I am showing right now, this picture we will use throughout the today's 2-hour session, because this is the main configuration for the nuclear and particle physics nuclear shell model basically. Okay, so there in the last class one girl was asking about the magic number concept. So magic number concept will come from this bracket, I mean square, this square box you can see. So this is 2, 8, 20, 28, 50. So these are nothing but the numbers for n. If the neutron number or proton number is like that, let's say proton number is 2, 8, 20, 28, 50, these numbers will call magic number. Why it will call as magic number? And obviously the same is for the neutron also. So if proton number will be 2 to 8, 20, 28, 50, then this type of compound will have the magic number as proton. And similarly for neutron, as these numbers, it will be as a compound with a magic number. So magic number is nothing but it will give a more stability to that compound, to that nucleus. Okay. So why it is like that? Because you can see this is the fulfilled state, nuclear state. Here also if I consider 1p, then okay, so 2, then 4, then 2. So as a whole the 8 will come. So up to this it is another complete nuclear state. So the 1p will be totally full, 1s will be totally full, as a whole it will come as 2 plus 4 plus 2, that means 8. So that means if our nucleon has a number as 8 or 2, that means it is totally stable. Okay, so that's why if it is a totally stable nucleon, then we can have a very high binding energy or something. So magic number is nothing but which will give a more stability to that nucleus. So the magic number is 2, 8, 20, 28. How it is coming? Obviously we can understand from this figure itself that 1 is fully filled, that means 2. 1p, 1 is 1p are fully filled, that means 2 plus 2, 4 plus 2, that means 8. Now coming to the 1D, 1D and 2s are little bit overlapping here, right? So if 1D and 2s are fully filled, that means up to here it was 8. Up to here the point was, the nucleon was 8. Then after that 8 plus 6 plus 2 plus 4. So it will give us 20. So up to this all the states, nuclear states are fully filled. And obviously you can see that if I go from 2s to 1f, then there is a big difference, right? So if all these states are fully filled, that means the nucleon are very much stable. Now coming to the 2s state, f state. F state also you can see that for 1f state, 1f 7 by 2, this state is little bit far from this other states. So whatever this will come, that will also give a stable nucleus, right? So 20 plus 8, 28. Now coming to this state. These all states are little bit overlapping to each other, right? So that means 2p, 1g, 1g, one portion of 1g is a little bit very overlapping with each other. So that means 28 plus 4 plus 6 plus 2 plus 10. As a whole, it is giving us 50. Now obviously you can understand, you can also say that okay, up to this it is fine, but after that also we can have a little bit more gap, and after that there is a overlapping of all the energy states. So why should not I write here also the number? So obviously you can write the number as a magic number here also. You can see here this is 50 plus 6 plus 8 plus 2 plus 4. So how much it will be? It is like 10. This is 10. This is 50. So it is like 70. So 70 can also be there, but the main thing is that we are not considering here more nuclear states other than 3s. Obviously there should be so many nuclear states other than 3s also. Up of the 3s also there will be so many states. So if I just consider these things also, then also we can have some numbers here. But whatever till now we are considering in our calculation for the nuclear and particle physics in NPTEL course, we will not go more than 50 nuclear number. So we will just focus up to this one at least, and after that we will see if in any exception we will see the nuclear number as a more than 50, then we will go to these states also. Okay, but these states are also there, as well as after above of these states also there will be so many states. So there is no problem on that. So up to this one we are just considering right now, but obviously there will be so many more nuclear states after this. Okay. So the magic number is coming. The magic number concept is coming from this nuclear cell model itself, because nuclear cell model only can tell us that y2, 8, 20, 28, 50. These numbers will give us more stability, because this can be explained through the nuclear cell model, and these numbers are nothing but the closed nuclear cell structure for, let's say, 1s, 1p, 1d, 2s, and 1f, 2p, and 1g, some portion of 1g also. So that's why we will tell these numbers as a magic number. Now there will be a question also that bimagic number. Bimagic number is nothing but, let's say, in any nucleus, n is 8 and p is, let's say, 20. So this is also a magic number, this is also a magic number. For neutron and proton, both are magic numbers. So that means it will give us bimagic number. Nothing but like that. So if only one of the neutron or proton is having a magic number, then we will have the compound as a very stable. But if n and p both are having the magic number, then it will call as bimagic number, which will be more stable than magic number, because obviously you can see that n is also fully filled, p is also fully filled. So obviously there will be too much energy. For breaking the nucleus, to separate the nucleons from each other, we will have to put too much energy inside the nucleus so that it can separate. Otherwise it will not be the separate one, because it's a very stable nucleus if the neutron and proton are in the magic number continuation. Okay, so this figure we will use throughout our lecture today. So I just want to paste that one, because if anyone will stuck on the nuclear cell configuration, then they will come and they will see this one. So this is nothing but this means that this one is the lowest energy state, then after that this is the second lowest, this is the third lowest, like that there will be a higher order terms, right? So in the last class also, how I have written, I wrote here like 1:2, then as a whole 2, I wrote like that. So what does this means? I think you all remember the meaning of this notation. So 1 is the principal quantum number, S is the value of L. If L equals to 0, then it will be S. Half is nothing but the spin, and this is the number of nucleons in that energy state. So you can see that for 1s, maximum 2 nucleons can be present here. So if I just pictorially write it like that, because of the Pauli's exclusion principle, one should be speed up and another should be spin down, and that's why this 1s has maximum 2 nucleons in that energy state, in that nuclear state. So this is the picture. So we will use that one. So just come to the first question. If anyone has any doubt, you can just unmute yourself, as I already told for the first class also. So if anyone has any doubt, you can just unmute. Otherwise, if you will write something in the chat box, maybe I will not be able to see that one. Then you can just unmute yourself and ask the question. Okay, so the first question: what is the expected spin value of the ground state of the nucleus N715 within the nuclear cell model? And there are a little bit options: 0, half, 1, 3/2 and all. So for this question, this is very similar to the previous week's, I think last question. So just let me go through this one. N715. Whoever was not present in the last class, maybe I can explain that one a little bit more, this question, and after that whatever the next question will be there, I'll just go through that one and we will just do very quickly. Okay. So this question I am just going to write explicitly so that we can understand thoroughly. So N715. So N715, what does this means? Obviously, if I see this notation, then directly I can write the neutron number and proton number. Proton number is 7 because it is given here, and neutron number will be 5 minus 7. So if it is 5 minus 7, then it is coming as 8. Okay. So now come to that plot at least. Okay, let me just remove all these things because it is coming as a very hazy thing, as this is the main picture for today's class. So it's better to remove these parts. Okay, you can see the recorded video later also. If you have any doubt, you can just go through this video, and after that you can just send a question in the feedback forum. I think there is a feedback forum, so you can send your question there also. So let me remove that one so that we can understand. Okay. So yeah, so here you can see, as I told last time also, that if a neutron, if any nucleon has the even number, so that will not contribute to the spin value or parity. But if it has a odd number, then it will contribute to the spin as well as parity. So why I told like that? Because if for N715 we got the neutron number as 15 minus 7, which is 8, right? So if it is 8, then you can definitely see from this figure that 2 is there, and up to this 1p, 8 has already filled. That means for neutron case, 1s and 1p, these two nuclear states will be fully filled, right? So that means what? That means that it's our neutron. Our neutron is fully filled and it is a very stable particle for this case, right? So who has left? The left is like proton number. Proton number was 7. So if it is 7, then you can see obviously first 2 nucleon will come in one S state. So we will focus right now on proton only. Let's say I am writing here proton only. So 2 proton will come here. Now come here. Here means like there is 4, right? 4 proton can stay here, and I have total 7 proton. So 2 has already gone. 4 will come here. 1, 2, 3, 4, right? Now come to here. So if there is 4 and there is 2, that means as a whole 7 proton has already gone. Only 1 proton has left. So if 1 proton has left, then obviously there is no other option to put here. Then that means the other higher state will have only 1 proton. So the other higher state means the state is 1p half. This state is not fully filled because this is halfly filled. The maximum capacity of this nuclear state is 2, but as we have only 7 proton, that means it is coming as 1 and there is 1 vacancy, right? So that means this one is the main responsible to give all the spin and parity for this nucleus N715. Okay. So now coming to the question. Question was, what is the expected spin value of the ground state of the nucleus? So obviously each and every time I will not give the figure whatever we have shown right now. So we have to little bit remember these things. 1p 3 by 2 4, then 1p half and 1, because 2 plus 4 is 6 and plus 1 7. So this is as a whole 7 protons, 7 protons. Okay. So that means which one is the main responsible nuclear state? Main responsible nuclear state is 1p half. Now how many knowledge we can get from this nuclear state? Obviously the N is 1 for this nuclear state. P means our L, that means orbital angular momentum, that is equals to 1, because L was 0, that means S, L was 1, that means P, L was 2, that means D, like that. Okay. So if it is the P state, that means L will be 1. Now coming to half. Half is nothing but this is giving the spin value. Spin value will be half. Now here it was 1 because only 1 proton was there, right? So that means our spin for N7 15 will be, the spin will be half. And parity, let me check here parity. What will be the parity here? Parity is nothing but minus 1 to the power L, right? So if I write here minus 1 to the power L, L is 1 for this case. So it will be negative. That means odd parity. In that question they are not asking about parity right now, but they are just asking that expected spin value of the ground state. Obviously we are talking about ground state. If we will talk about excited state, then what will happen we will see later. So the value will be half, that means B, spin value. Yes. Okay, so I think I have already explained very clearly for the first question. If you have any doubt for the first question, you can just ask me right now, or you can ask me later also. Whenever you will feel free, then you can ask me. I think I am audible to all of you. Okay, fine. So, okay, then we will go to the next question. So for this case, spin was half and parity is negative. So I have also written here in the keyboard notation. For N750, number of neutrons are 8, which is even half filled, and number of Actually it is not half filled, it is full filled. So the number of protons are 7, so the orbital configuration for the nuclear state is this one. So therefore the spin of the ground state is half, which is the correct answer as B. Okay. Okay, fine. Now coming to the next question. Question number 2. What is the expected spin value of the ground state of the nucleus within the nuclear cell model? So this is exactly similar whatever we did previous question. So let me write here quickly. By seeing that notation, obviously you can write n and p value. P value will be 20, n value will be this one, so which is 23. So here obviously you can see that p is even, so that will not give that much it will not give any contribution to spin and parity, but n will give us contribution because it is 23. Now we can come to the plot, this figure, so that it will be simple to understand. Let me again erase that one a little bit so that you will understand clearly. So what was the n and p? There p was 20 and n was 43 minus 20. So now see, 20 means up to this one it has already done. So that means for p these all states are fully filled, right? Now coming to 23. So if 23 I am writing, that means what? I have to write all these things. 1:2, 1p 3/2 4, 1p half 2, 1d 5/2 6, 2s half 2, 1d 3/2 4, then 1f 7/2 3, because 3 was left. 23 minus 20, that is giving us 3. So 3 neutron was left, so that will go in this nuclear state. But the thing is that the maximum capacity for this nuclear state was 8, but we are putting here only 3. That means 5 vacancies were already there. So the spin for calcium 2043 will be 7/2, and parity will be how much? Okay, the F is there, the latest one is F, right? So F means what? F means, where should I write? L equals to 0s 1p 2d 3f, okay, spdf. So that means minus 1 to the power 3, which is negative, which is odd. So the parity for this case, it will be odd, but maybe they are not asking about parity. Yes, they are not asking about parity, they are just asking about the expected spin value of the ground state of the nucleus within the nuclear cell model. So it is 7/2, because we have seen that 1f 7/2 3 was the last nuclear shell configuration. Maybe I did not write it, it is in that form. Okay, fine. So the correct answer will be 7/2. Okay. You can also do by yourself, so that you will have a flavor of this. 20 and 23. 23 is the most important one. So this is the thing. 1d 5/2 6, 1d 3/2 4, 2s half 2, 1f 7/2 3. Now add these things. 2 plus 4 6 plus 2 8 plus 6 14, 14 plus 4 18, 14 plus 4 18, 18 plus 2 20, 20 plus 3 23. Okay, that's why it is coming as 23. Okay, fine. Now maybe we can go to the next question. What is the expected parity of the ground state of the nucleus in cell model? Okay, so parity they are asking. Okay. For this case, proton is 14, neutron is 29 minus 14, 5, 15. Okay. So 15 is the neutron number and 14 is the proton number. So maybe we will go again to that figure. I'm telling you that you have to just remember this nuclear cell structure so that you can understand you can have the correct answer for all the questions. 14 and 15, right? Okay. Okay, so P was 14, N was 15. Now see 14. 14 means this is 2, this is 4, this is 2. As a whole, it is 8. Then how much is left? 6, right? So if I am taking this one, then 8 plus 6, which will give us 14. So up to this one we need to go, up to this. For proton case, up to this we need to go. And it's already fully filled because for 1D, maximum number of nucleons should be there as 6. So 6 is already filled by that 6 protons, and these all are fully filled. So obviously for 14 as P, this is fully filled. Okay, so that it will not give any contribution to spin and parity. Now coming to 15. 15 means up to this one it was 14 for proton. The same thing will come from for the neutron also, but there is one state, 2s half, and then there will be 1 because 15 is there, right? So 2s half 1, this is the main responsible for giving the parity as well as spin for silicon 1429 nucleus. So if it is like that, then our L will be 0 because L will be 0 for A state. So that means the parity, they are asking for the parity. So parity will be minus 1 to the power L, that means minus 1 to the power 0, which is giving us positive value. That means it is giving us even parity. So coming to the question, yes. So for this case, whatever these things that we will need to write, 2, 4, 2, as a whole 8, then there will be 6, then there will be 2s half 1. So as a whole it will be 15. And the main responsible is 2s half 1. So for that case, minus 1 to the power L is parity, and L is here 0 for S state. So the parity will be minus 1 to the power 0, which is positive. That means even parity. Okay. So it is coming as even, this one. Okay. If there is no other questions, then we can go to, here also I have written there. Okay, fine. 1:2p2, 2p, 1p half, 1d5, and 2s1. So 2s1 means L equals to 0. Therefore minus 1 to the power 0, that is even parity. Correct answer is A. Very good. So this is up to the question number 3. Now we will go to the question number 4. But before going to the question number 4, if you people have any doubt, you can ask me. Or otherwise we can go to the next question. Okay, fine. So the next question is question number 4. What is the expected parity of the ground state of the nucleus Mg1225 in cell model? So just focus one thing. We are not taking care of any excited state till now. We are just focusing on the spin and parity for the ground state of this nucleus, right? So till now also this is the ground state for the nucleus Mg1215. So right here Mg1225, not 15, 25. So for this case, quickly I am just writing here P equals to 12 and N equals to 25 minus 12. So which is nothing but 13. So as it is 12, so let me go here again. I think it's already done for everyone. I mean, you should remember that one so many, because I have written this so many times. Something was 12 and something was 13, right? For Mg, the neutron was 13 and proton is 12. So proton is 12. So if it is 12, that means 2 is there, then 4, 2 as a whole, it is 8. Then, okay, after that you can see 12 minus 8, that means 4. So 4 will go here because this is the lowest one. After that it will go here. But 1d 5 by 2. The maximum capacity for this nuclear state is 6. That means what? One can do like that, one can do like that, and one can do like that. But for Mg 1225, only 4 protons are left. So that means they will come here as well as here. And this state and this state will not be there, right? So there will be one vacancy here. But the vacancy is in which sense? You can see whatever the L and parity will be there for this, that is totally cancelled out for by this. Similarly for this one also, whatever the parity and spin will be there for this particle, this nucleon, that will be exactly cancelled by this one. So that means even if it is 1d 5 by 2 state is not fully filled, but also it is not contributing any type of spin and parity calculation for our question, as it is coming as, I mean, it is coming out as pair. Okay, this is a pair product, this is a pair combination, this is a pair combination. So even if there are two vacancy, but it will not contribute in our spin parity calculation for Mg1225 nucleus. The only one which will contribute, that is 13. That means the neutron number. The neutron number is 13, so that will give us a contribution for the spin parity. Why? Because you can see, as I have already written, for up to 12 it will be purely full, but for the 13th one, 13th will be where? 13th will be here only, but only one nucleon will come. I mean, only one neutron. For this case it will be neutron. So only one neutron will come and one vacancy will be there. So if it is like that, so whatever the spin is there, that will not be cancelled by another one. Okay, so that means this will contribute to the spin and parity calculation for our Mg1213 nucleus. So let me just quickly go there in that question number 4. Yes. So here it was like this, it was this. For this one is half 2, 1p 3 by 2 4, 1p half 2, 1d 5 by 2. Now see, 1d 5 by 2, then 4. 2 plus 4 is 6, plus 2 is 8, plus 4 is 12. Now for 13 the same will be there. But 1d 5 by 2 5. But 5 is, this one is the main one. So they are asking about what? Expected parity. Okay. So parity will be governed by this nuclear state. So if it is like that, then what will be the parity? The D is nothing but L equals to 2. Okay. So if L equals to 2, that means parity is minus 1 to the power L. So minus 1 to the power 2, which is giving us positive. That means even parity. Okay. So this will give us even parity. That means the first one. Just focus on this one. We will only focus on ground state till now. If there is excited state, first excited state, second excited state, then we will have to think a little bit more. So I have these questions also in my question list. So we will go through that one slowly. Up to this, I think all the questions are fine to all of you. I hope so, because there is no such questions coming here. Can you follow me? I mean, whatever I am telling, is it followable? Is it understandable by all of you? I mean, at least one can.
Yes, ma'am, it is.
Okay, fine. Okay, then we can go to the next question maybe. Yes. Within the nucleus, now you can see. Within the nuclear cell model, this is the model, sorry. Within the nuclear cell model, speed and parity of the first excited state of C613 are most probably. Now see, first excited state. This is the little bit tricky, obviously not that much tricky, but we will see. First excited state, till now whatever we did, that was for the ground state. So for ground state we don't need to do anything, right? But for first excited state, let me write first C613. So obviously by seeing that one quickly I am writing here proton equals to 6 and neutron equals to 13 minus 6, which is 7. Okay, I can write that one clearly. Very good. But this is for the ground state configuration, right? Okay, let me first do the ground state calculation, and after that we will go for the first excited state so that it will be clear. So let me draw that figure, whatever we did there. I'm just drawing here 1s. For 1s there will be only 1, which is 1s half, right? Then after that there will be 1p. For 1p there is 2 states. 1p 3 by 2, 1p half. Okay, so the maximum, I'm writing here the maximum number of nucleons. This is 2, this is 4, and this is again 2. Okay, now coming to 1d. So for 1d case it is coming as 1d 5 by 2 and the maximum number is 6. Then there is something, but the 2s is also coming here. So let me write here 2s. 2 is half and this is 2, but for this case it is 1d 3 by 2, which will give us 4. Now see the number, it is 2, then up to this one. Okay, obviously there will be more spacing between these two, but okay, fine, like for this calculation it's fine. So it is 2, then 4 plus 2 as a whole, this is coming as 8, then 6, 4 as a whole, that will come as 20. Now as carbon is present here, carbon 613. So carbon 613, that means we don't need to go beyond 20 obviously, because proton is 6 and neutron is 7. Now see the ground state. First of all I am just talking about ground state here. Okay, ground state you all know how to write here, because ground state means P6 is there. P6 means, like, let's say proton is 6 even number, so that means we are not going to do this calculation for proton, because 2 and 4, these are all together will give us 6. So we are not bothering about proton till now. We will bother about neutron, right? So now coming to the neutron. So neutron will come here for ground state. Okay, just remember for ground state what will happen. For ground state it will come here and here, then here 4 will be there. So as a whole 6 has already done. 1 is there left, which will go up. because this is the maximum number of nucleons here for 1p3/2. So the fifth one, the seventh one will go here. So this is for ground state. Now let's check what will happen if the first excited state will come. Now just think, okay, I'm just writing here, this is for neutron. Maybe I can change my color. Yes. Now for proton, for proton what is happening? For proton, this one was there, and here in that state, like in that state, 4 proton was there. So proton is nothing but in red color, and there was no proton in ground state. Okay. Now for first excited state. For first excited state, what will happen? If this is the condition for the ground state, then obviously by seeing this nuclear structure, it is very similar to the atomic structure, as I already told previous class also. Now you can see, as for proton case, ground state is like that, where 1s is totally filled, 1p3/2 is also totally filled. For these cases, if the first excited state is coming, p will not go in the higher state because it's already stable, very much stable, right? So if first excited state means what? First excited state means we are just giving a little bit more energy from the outside to the nucleus so that it will come to the higher energy level. But for P, as it has already fully filled case, it will not go that much easily to the higher energy state. Okay? But coming to the neutron, for neutron case, you can see this one is fully filled. It will not go. This one is also fully filled. It is also not going to go. I mean, because these all 6 neutrons are fully filled and they are very much stable to each other. But the main thing is this one. This one is only one present in that energy state. So if we are putting some external energy to this nucleus, what will happen? This lonely nucleon can go to the upper state. Okay? Because it is loosely bounded. It is not that much strongly bounded. So this will go to the upper state. Upper state means, let's say this is going here. So the last neutron will go to the next higher nuclear cell. Okay? So that means for the first excited state of carbon 613, the main responsible nuclear state for spin parity will be not 1p half, it will be 1p3/2. 1p half was for ground state, but for first excited state, the responsible one will be 1d5/2. Okay. So for carbon 613, first excited state, last nuclear cell configuration will be what was that? 1d5/2. 1d5/2 1. Why 1 I am writing here? Because the last one, what was there in 1p3/2, that will come right now at 1d5/2 nuclear state, because it is the first excited state. Okay, I think you understand. Now the question was spin parity. Okay, fine, spin parity. Now obviously, as I already got the latest responsible nuclear state, then from that we can simply tell that what will be the spin and parity. So simply the spin is like 5/2 and the parity will be -1 to the power L, and for D, L equals to 2. I'm just writing here so many times because L equals to 0 is S, D, F. Okay, so L equals to 2. So -1 to the power 2, which is positive. That means even parity. So the spin and parity will be, spin is 5 by 2 and parity is plus. Actually the spin parity we can write it like this notation, J pi. So the spin parity can be written as like 5 by 2 then plus. Okay, so this is the notation for simplification, compactified notation, but still fine. Yeah, so actually here there is no 5 by 2, so this is not correct option. I mean last year there was a mistake, so I just put that one blindly, so obviously sorry for that. So there will be a 5 by 2 and then even. Okay, so the C option will be there. So I hope you can understand this one, that why it is coming as 5 by 2, because it is coming in the higher level. Okay, now okay, maybe I can ask in the next question the question, I mean I can discuss this in the next question also, but just for a completeness, in the first excited state what happens? First excited state means like this one has gone to here, right? Now coming to the second excited state. So for second excited state what will happen? Whether that will go here or any one of these will go here, that is a question, right? So for this, to answer the question, we have to see what is the difference between these two nuclear states, what we are talking. I mean from this figure obviously you can't see any type of exact nuclear distance, as I have just written here by my hand, but we have to come here to see this one. Yes, now just let me erase these things. For first excited state that is fine, but let's say for second excited state what will happen? I mean which one will come to the next higher energy level? For that case we need to check which one will be the smallest distance. That means, let me write, that means, see here, two was there, right? I mean there was only one, I mean for C6 13, 2 and 4 was fully filled and the 7th one was here for the ground state. For first excited state obviously it will go here, no problem, but for the second excited state you can see this one was here and this one was here, right? But for, and right now in the first excited state this is the scenario, but for second excited state, let me just, for completeness I am telling, because obviously in some questions they are asking about the second excited state also. For second excited state you can see this can go here, one of these can also go here, but from the figure you can see this distance is little bit small than this distance, right? That means more energy will require to put this nucleon from here to here, but less energy will require to move one of this nucleon from here to here, because the nuclear difference is little bit smaller here than this one. So for second excited state, again what will happen? This one will be here and one of these four, one will come here and 3 will stay here. I mean I am right now not talking about the second excited state for carbon 613, because the question was only for up to first excited state, but for the completeness case I am just talking that what will happen in the second excited state. Okay, so for this second excited state also we have to think about these energy levels, what is the distance between these energy levels. Depending on that, which one will give the minimum energy level distance, that will come into picture. But obviously first of all the time the lonely nucleon will give a, I mean will have a first priority to go to the next higher level state. So maybe where we were, yeah, we were in the question number 5. Yes. Now we can go to the question number 6. Within the nucleus cell model, again mode. Okay. Spin and parity of the first two excited states. See, now they are talking about first two excited states. That will be little bit more interesting, because here they are asking first excited state as well as second excited state. Okay. So just come here. Mg 12, 25. Proton is 12, neutron is 13 because it is 25. So if proton is 12, okay, we will write here 12 and 13, right? So yes, here proton was 12, neutron was 13. They are asking first excited state as well as second excited state. So first excited state. At the very first, the ground state we are talking. So proton means 12 means 2, 4, 6 and 2, it's 8. Then 8 and then there will be 4 for proton. But for neutron, there will be 4 as well as, actually there will not be 4. For proton there will be 4, but for neutron there will be 5 for ground state. Right? So let me write here, only this I am just drawing here. Okay, so this is 1d 5/2. For neutron case, 5 neutrons will be there. So how it will come? It will come like that, and 1 will be there for the ground state. Now coming to the excited state, first excited state. As I already told, if it is a lonely nucleon, so obviously it will go to the higher level. So it will go to the higher level. Higher level means in which level it will go? It will go to the 2s half level. Okay. So whatever it was there, that will go to the 2s half level for neutron. Why proton is not coming into picture right now? Because it's already fully filled. Okay. So to break these nucleons, we need to push we need to push much external energy. But before that, obviously this is coming to this state, and it is making as first excited state. So for first excited state, which one is the critical nucleus cell structure? That will be 2s half 1 for Mg 1225. Very good. So for first excited state, spin parity I think they are asking. So spin is like half, and parity will be -1 to the power 0. So it is even. Okay. So parity is even and spin is half. So for first excited state, it is like half plus. Okay, fine. So maybe we can quickly go to the question. What was the question number 6? So for first excited state, Mg 1215 will have half plus. So either A or B. Among these two, one can be correct one, because C and D are giving the wrong value. 5/2 5 is given. So obviously half plus will be the correct one for first excited state. Now coming to the second excited state. Okay. It was 1d 5/2, and there was like that, this one and this one. It was for ground state. For first excited state, this one was come to here, it was 2s half. This is first excited state. Now what will happen if the second excited state is coming? Okay, very good. So again maybe we will go there, because for this case we need to check which one is which one is giving the lowest energy level, right? So as I told here, for the first excited state, what is the case? Let me write here. First excited state. For the first excited state, there was 1, 2, 3, 4 and 1. And all these are fully filled. These we are not taking care right now. So now you can see either this neutron can go to the higher level, or among these 4, one can go to the higher level. But can you tell me by seeing this picture in the second excited state which one is most probably go to the higher level? Will it be this one, or among these 4 one will go here? Can anyone unmute yourself or tell me which one should go in the second excited state? This one, or among these 4 one will go?
Ma'am, the already excited one in the first case.
This one, right? That 2s half.
Yes,
Because
ma'am. 2 1
because
D3.
yes, because the difference between these two energy levels are very small with respect to here to here. Okay, so that means in the second excited state, let me write here the second excited state configuration. So second excited state, the second excited state configuration will be like 1, 2, 3, 4. This here previously it was there, but right now it will be here. So what will be the final configuration for this second excited state? That will be 1d 3 by 2 1. Now you can obviously definitely see what will be the spin parity for the second excited state. So the second excited state will have spin as 3 by 2, parity as, okay, d means it is L equals to 2. That means minus 1 to the power 2, which is positive. So 3 by 2 plus, right? Now coming to the question again. No. Yes. So I told you that either this one, I mean A or B will be correct, because half plus was there for the first excited state. Now we already concluded that for second excited state, the energy is like 3 by 2 plus, I mean spin parity. So that means the B option will be correct one. Okay. Okay. So I think I have already written that one. Yes. Yes. Correct option is B. And I have already written the nuclear configuration for this second excited state also. But if I just want to explain that one qualitatively, then we have to see the energy levels and their differences, so that we can confirmly tell that what will be the second excited state and what will be the configuration for that. Okay. Okay, so now maybe we will go to the question number 7. Yeah, so till question number 6, whatever it was there, that was totally based on the nuclear cell model, as I already told. And I think in the last or previous last question, it is also the cell model question. But yeah, fine, we will see that. But obviously always just keep in mind that we have to remember that structures and the energy difference, energy level differences between these states. Then we can answer all the questions about nuclear cell model. Okay. Okay, fine. Now come to the question number 7. In the question, it is saying that consider the classical case of a particle of mass 3.2 into 10 to the power minus 30 kg and charge is 1.6 into 10 to the power minus 19 coulomb, which is moving in a circle with angular momentum 2 into 10 to the power minus 34 joule into second. The magnetic dipole moment associated with this is how much? Okay. So whatever the data has been given, I am just quickly writing that one, and after that we will find the answer. So Q has been given as 1.6 into 10 to the power minus 19 coulomb. Yes. Then mass is 3.2 into 10 to the power minus 30. So M is 3.2 into 10 to the power minus 30 kg. Okay, very good. Then angular momentum. Angular momentum can be written as L, let's say. So it has the value 2 into 10 to the power minus 34 joule into second. Okay, so AM is given, Q is given, L is given. Now they are asking what will be the value of magnetic dipole moment. Okay, so mu. uh, See, if I just want to put the values in mu, then obviously it will come directly the answer. But if you want to understand the question a little bit physically, then what will happen in the physical meaning? They are saying that one particle with mass something and charge something, it is moving in a circular path with the angular momentum this much. So if it has a, let's say this is a particle and this particle is moving in a circular path, and if it is a charged particle, then obviously this charged particle, if it is moving in a circular path, then it will produce a magnetic field, right? So what will be the magnetic field for this particle that they are asking? So what will be the expression for mu? I have already written here, you can see that this one. This is nothing but half QVR. Now if, okay, I am just coming here right now, as we have already seen that mu equals to half QVR. Now one may ask me, I have Q, I don't have V, I don't have R. So how can we calculate the value of mu with the help of M, Q and L? So we need to put a little bit trick on there. What is the trick? See, L is nothing but MVR. L is MVR. So if I write here MVR, so then Q, then one M has extra as the multiplication in the denominator. So for numerator. So in the denominator also I have to multiply one M. So it will have half LQ by M. Do you understand the point? Like we have these values, we have these quantities, but for the mu calculation we need V and R. So to get V and R value, we will do some trick that we will just multiply M and divide M. Then we will have the value half LQ by M. Can you hear me? I hope so. Okay. So now you can understand. Here it is L, here it is Q and here it is M. If L, Q and M are given here and you just need to put all these values, then you will get quickly the value of mu. So I have written here the value here as well. So you can see the value is mu equals to 1.6 × 10 to the power minus 23 ampere into meter square. Okay. So maybe it's fine. Then we can go to the next question. Yes. See this question. In a scattering of electron of a nucleus, electrons of energy equals to 10 MeV are used. If these electrons are represented by the wave function phi equals to a to the power I k z, where the position coordinate is along z axis direction, the value of k is how much in meter inverse unit? Just see the unit here. Obviously the units should be very much important for physics calculations. So the energy is given in MeV, but the answer they are asking for in terms of meter inverse. So we have to be very much careful about this. Okay. Now I have already written the result, so maybe I don't want to explain that one more because it's a very simple one. You can just see the question's answer. Electrons are represented by the wave function phi equals to a to the power I k z, where the position coordinate is along z direction. Right? For the plane wave, the energy momentum relation is given by E equals to h bar square k square by 2m. It's fine, it's coming from the quantum mechanical system. So if it is like that, A equals to h bar square k square by 2m, we can have the value of k as, k is nothing but the wave number, right? So k will be right root over 2me by h bar square. Now putting the given values of E, M and C and h bar. Actually they were talking about electron. So that means the mass of the particle will be electron mass. Okay. So here if I just put the value of M as 0.511 MeV, that is also fine. And C is 3 to 10 to the power 8 meter per second. Why C is needed here? Because E is given in MeV and we are putting AM as in the unit of MeV also. So by putting all the energy, unit conversion factor and all, we are finishing with the result in meter inverse, and the answer is 1.61 into 10 to the power 13 meter inverse. Just try to calculate by yourself this question. If there is some problem in the energy conversion factor, the unit conversion factor, then obviously you just let me know. I don't want to calculate that one right now by my hand because it's a very simple thing, like only 2, then multiplication of 0.511 into 10 to the power 6, and if it is in EB by C square, then we have to multiply that one with C also. Then after that 10, then 10 into 10 to the power 6 EB, then divided by h bar is 6.58 into the minus 16, and then whole square, then has a whole root, then it will come as meter inverse. Okay, so should we go to the next question? I hope so, because there is not that much cruciality in that question. Okay, maybe I can go to the next question. Next question is this one. You can see in that slide. In experimental measurement of the orbital angular momentum of deuteron, 10,000 samples were selected. Approximately how many of them would have measured L equals to 0 h by 2 pi? So that is the question. So what does this means? What does this question means actually? The question means that, I think I am not able. The question means that if there is 10,000 samples for any experimental measurement of deuteron, among these 10,000 samples, how many will have orbital angular quantum number as 0 h bar. H by 2 pi is nothing but the unit. Okay, don't bother about these things. So L equals to 0, that is the thing. So how many samples will be for L equals to 0 and how many will be for L equals to 2? Because in the previous class, I think you have remembered that one, that for the deuteron is not a pure angular momentum state. It has the mixture of angular momentum L equals to 0 as well as L equals to 2. Okay. So that was L equals to 0 and L equals to 2 state. But the percentage was like L equals to 0 is around 96%, L equals to 2 is around 4%, like that. Or did I write it correct? No, I write correct. So L equals to 0 was 96% and L equals to 2 was 4%. Now you just understand, I have 10,000 samples. Among these, L equals to 0 can be with 96% sample, and L equals to 0 can be with 4% sample. Okay, so if it is like that, then among 10,000, what will be the 96%? 96% means 96 divided by 100 into 10,000, right? So it is like 9600. So 9600 sample will be with L equals to 0 state. Okay, this they are asking, this one they are asking approximately how many of them would have measured L equals to 0. So it will be simply 9600, because around 96% is L equals to 0 state. And I have written this one also here, but I have written it a little bit different way. You can see that deuteron are found in two states, L equals to 0 and L equals to 2. Therefore, deuterons with L equals to 2 will be that much. So 9600 samples will be with L equals to 0. That's it. Right. Okay. So maybe we will go to the next question. In an experimental measurement of the orbital angular momentum of deuteron, 1000 samples were selected. Approximately how many of them would have measured L equals to 2? So exactly similar question, but the difference is there. They were asking about L equals to 0. How many of them will be? But right now they are asking about L equal. So 10,000 sample was there. So L equals to 2 means obviously it will be, as we have already calculated, that 9600 were for L equals to 0 state. Now 10,000 minus 9600, that means 400 will be for L equals to 2 state. Okay, so the answer will be D. Can you hear me, by the way? Hello? I was out of the network, right? I did not know that when you got disconnected. So can anyone tell me up to which internet connection was there and after that I got disconnected? Hello?
Ma'am, I guess up to here it was fine, ma'am. After that, it sort of disconnected.
So where it was, I mean, up to which portion I was disconnected, like that L equals to 0 samples you got, or no? I mean, that question you heard? Have you heard this question that 10,000 samples were there and L equals to 2 or L equals to 0, how many state samples will be there?
Yes, ma'am. Middle part, we heard. Yes.
Okay, fine. Okay, then it's fine. So maybe this question also has also you understand, like, I mean, this is very simple, like L equals to 0 as what is happening here? Array? I don't know why it is I don't know why it is coming disconnected quickly. Okay. Okay, so I think this question has been already discussed, that why has the 400 samples, because as we have already known that L equals to 0 was the 96%, So it was like 96,000, 9600 was the L equals to 0 state. So obviously the rest of the sample will be L equals to 2 state. Okay. So now coming to the next question. I have already written. Yes. My laptop is getting hang. My laptop is getting hang. Hello, my laptop was getting hang, so that's why maybe I was disconnected again. So sorry for these things. I hope you can see the screen that predict ground sheet spins parities of this one. Is it
Yes,
visible?
ma'am.
Okay, fine. So I'm really sorry because the internet, the laptop was getting hang in between of that. Okay, so this is the last question. Just see that one. So this question is like exactly similar whatever we did for the rest of the classes. So the ground state spin and parity of the three nucleus. Aluminium 1327 is 1633 and argon 1841. Okay. So for this case, obviously, first of all, aluminium 1327, that means P is 13, N is 26 minus 13, so it will be 14. So obviously N is an even number, so it will not contribute anything, so P will be 13. So I just go through that one right now quickly. 1P 3 by 2 4, 1P half 2. Now you can see 2 plus 4 6 plus 2 8, and then more okay 5 for 5, so it is 1D 5 by 2. So 1D 5 by 2 should be there. So as it is not fully filled, so that will be the main responsible one for the spin parity. So the actual one is like 1D 5 by 2, so the spin will be 5 by 2, and L is 2 for the D states. So parity is minus 1 to the power 2, which is even parity. Okay, got it? So that means for this case it will be 5 by 2 plus. This is okay. One more thing, if there in that question there is no mention about the ground state or excited state or any type of first excited state or a type of things is not mentioned, that means they are supposed to ask you the question for the ground state only. But as in that case it is already written as ground state spins, so obviously there is no confusion. But if there is no ground state like thing was written, but still you can understand that it is for ground state. Okay. If it is for first excited state or second excited state, they will obviously mention that one in the question. Okay, now coming to this S1633. S1633. So proton is 16, N is 33 minus 16, so it will be 17. Now maybe we will go for the up one. 16 will not contribute anywhere, 17 will contribute here. So where 17 will contribute? 17, let me erase all these things, it's a very hazy one. So 17 will contribute where? So 17 will contribute here. Okay, neutron was 17, so that means 2 plus 8, 8 has already, that means total 8 was there, then it is 14, 8 plus 6 is 14, 14 plus 2, 14 plus 2 is giving us 16, right? Then after that it will come here, so that means this shape will be there, 1t 3 by 2, 1. So the spin will be 3 by 2, parity will be minus 1 to the power L, minus 1 to the power 2, which is positive, that means 3 by 2 plus. Okay. So for sulfur it is 3 by 2 plus. Where is that question? For sulfur it is 3 by 2 plus, and the next one is argon 1841. Okay. So for argon, argon 1841. So proton is 18, neutron is how much? 41 minus 18. Okay, so that is like R3. It is again getting stuck. 3, 2, right? So it is 23. So 23 will be neutron, and as it is a even number, it will not contribute anywhere. As it is odd number, it will contribute to the spin parity. So coming to the n equals to 23 case, for the up one, n equals to 23. So up to 20 it was there. After that this one will come. So 1 if 1 if 7 by 2, 1 if 7 by 2 will be there. One if one if 7 by 2. Again it is fine. So much problem. Maybe it's a connected. Only one question is left, but still. Array. It's too much strange happening. Okay, fine. So that was the last question. Okay. So the last question was that you have to just calculate the spin and parity of this aluminium sulfur and what was the next one? Aluminium sulfur and one more was there. So that one was the that was the last question. So till now, is there any question for today's session? Whatever we were discussing. Okay, aluminium sulfur and aluminium sulfur was there, and they were asking for the ground state spin. So obviously, all are familiar with ground state spin. So do you have any question? Do you have any question regarding today's session? Whatever it. Hello? It was fully unexpected, but every time I'm getting. I hope you can see my screen, right? Can anyone confirm that it is visible or not?
Yes, ma'am, it
Yes.
is visible.
Okay. I'm really sorry because of this, like internet issues and all. It was not internet issue, it was the hang of my laptop. Okay, so these 11 questions are there for today's session. So, do you have any type of doubt on these 11 questions or anything else? You can just ask me right now, or otherwise, so I will just go through all the questions one by one again so that you can remember the questions again and again. So this is the 11th question. You can see the screen. This is the 11th question. If you have any doubt on the 11th question, you can ask me. Then I'm going to start. That one was 0 and 2. Similar to the 0, how many will be there? The 8th question was is so there were so if you have
Ma'am, I had a doubt. So, ma'am, what if an element, both proton and neutrons are even numbers?
very good question. So for that type of things, for the ground state, if we consider about the ground state, in the ground state there will be no spin and parity for this singular state. Okay, that is 0 for spin is 0. As parity is like a to the big portion is equal to minus to the power 0. Plus, right? 0 plus. 0 plus. But if we are talking structure. In the neutral structure, if we have, let's say, n equals to 20 and p equals to 20. Okay. So what do you do? You do p equals to and p equals to. So this to mean it will be free field. For downside, as I told you, the field is 0, the variable is plus. But for state what will happen? For first state, it will simply as it is in two level, so it will go to the upper state. For civil, it will go for the product, but not for this time. In the first state, it will be considering, that means among these two nucleons, either nucleon or neutron or proton, among these two nucleon, let's say we are focusing only on neutron for proton. So neutron will go to the next higher order level. That means it will be p d by 2 for this state. The first state is, so maybe I think I can say here, so that it will be helpful for all of you. Let me try to save my screen and after that I will explain. No, I'm not able to show my screen. If I am going to show my screen, it will fine. So as it is also ending, I am trying to explain you very theoretically. See, if 1 is 2 with the ground state, excited state is 1 p 3 by 2. So for first excited level, the responsible free state will be 1 by 3 by 2, right? And that will be either for neutron or for proton, because in nuclear structure, proton and neutron both are floating in a similar food. I mean, there is no difference between nuclear and proton. Neutron and proton in nuclear structure. So any one of the nucleon can go from the ground state of their first, I mean, from their ground state to the first excited state, and we will have the first excited state immediately according to that. Okay. So if I was considering 1 is half 2, 1 is half 2 for neutron and proton in the ground state, for first excited level, any one of the neutron or proton will go to the next higher order level, which is 1 by 2. So 1 neutron or 1 proton can go to the 1 3 by 2 level, and according to that, the first excited state speed parity will be decided. Now coming to the second excited state. Second excited state will come like that. Like either this one will go to the upper one, or the first one will go to the next higher level, depending on the real speed. But so important part, like if it was zero, I mean even for the ground state there will be no speed parity, but for the excited state there will be some speed parity, and it will be dependent by the nucleon up level, like how it is coming to the higher level. So with that one, we can confirm that what is the spin parity for the first excited state. Am I audible?
Yes, ma'am. Got it.
Fine. For the high level, also you can see the characters whatever we explained in that question also. So, but for even with high level, ground state will not have this state, but it will be the spin state. That's it. So
Okay, ma'am.
yeah, is there any other question? Because I cannot share the screen right now. If I will do that over, then it will be correct. So eventually, so if you just remember questions and you can ask me any question, any doubt, you can just ask me right now. Or maybe we can
Yes, ma'am. I have one more doubt.
yes.
So when we are solving the questions, do we or do we not have to keep in mind the Pauli exclusion principle?
Yeah, Pauli exclusion is absolutely mind. Otherwise, how I was drawing one new question like let's say 1p3 by 2. 1p3 by 2 is maximum for nuclear can be there. So how they are saying that maximum for nuclear can be there? Because one is up, one is down, another one is up, another one is down. Pauli exclusion is nothing but different. So if one state is there as a up, another should be the down state. Otherwise, the Pauli exclusion will be violated. So each and every state Pauli exclusion principle should be observed there. Okay. So the first state, or let's say the last nucleus we are talking, the last nucleus is the loosely bounded nucleus. That is in only one case. Let's say 1p3 by 2. That was 4 axes. But as I have only one left nucleon, that will go to that 1p3 by 2 state. But there is nothing. There is no other nucleus. So yes, also nucleus was conserved because we are not putting these five nucleons in the same energy state. We are putting 4 at most for the side, and for the next one we are putting the one. So obviously each and every state all should be followed because these all are the fermions. The fermions should follow the exclusion principle and they should follow the Fermi statistics. So statistics also you have seen Fermi statistics who are following that they should follow the Fermi statistics. So every state Fermi statistics should be followed. Otherwise your prediction will be if it is not satisfied, in what we see by you, I can put 5 or 6 neutrons or 7 neutrons. That's not the one, right? So this is
Yes, ma'am, got it.
any other?
No, ma'am, no other doubt by me.
Okay, any other question? Any other? Finish our class 50 minutes before the timeline. So maybe if you have any doubt, you can ask me. Or anything if you want to ask me, write in the forum, discussion forum, I will see that one regularly and we will answer. I'm thinking that please all, I think some of you have already sent me the request to edit and edit the folder. So I already shared with you the folder. So if you review that one, review it so that you will see all the slides all the videos don't be have the review that one. So anything or maybe switch off here and we will show it. Maybe right now it's let's check once. I don't know. Maybe again I will not not to because again I know
Ma'am,
yeah,
uh, excuse me, ma'am.
sorry.
Can you, ma'am, I had a question regarding the number of vacant nucleon positions in each shell. Is there a fixed pattern to follow, or
There
are they just experimentally determined?
is a big pattern. It's the pattern coming from the equation to this one. Okay. This is nothing but the, I mean I could not see, I mean I have the scale right now. Yeah. See, given that configuration is 1/8 half, right? So I told you the principal point of the is diagram of the which is
Yes, ma'am. Yes, ma'am. Got ma'am. Okay, ma'am. Got ma'am.
Thank you, ma'am.
Thank you, ma'am.